Today we have was Laura at Parma, and then we got a PhD there as well.
Yeah.
And then we postdoc there as well.
No, I was postdoc in Jena, where I'm now.
You went back to Parma, or you went to Caltech?
I went to Caltech, and then I was faculty in Parma, and then
back to
yeah, sort of circle.
So he's won many awards and grants, including 2 ERCs. And his research is in numerical relativity and force and compact objects, gravitational waves, which is on structure.
Yeah, so thank you very much for the invitation. Many years ago, I was a bachelor student. I did my internship in this building. But then I decided that astrophysics was not really for me. So I kept on going with theoretical physics, and I worked specialized in numerical relativity and gravity. But then somehow I came back to it from another point of view. And so what I'm going to talk about today is our work. So it's about modeling general relativity, the problem of neutron star mergers. And the reason I think you all know is, well, we started much earlier than 2017 to do this work. Actually, we were always thinking about this problem. It remained a bit theoretical, hypothetical. But of course, now we have observation. And the idea is that if we have one or multiple of these events, like this one of August 2017, we will have plenty of data from gravitational wave to optical and high energy photons. And the idea is that to understand all this type of observation, we do need a first principle model, and well, we try to provide them. This is, I need to switch something. It's usually people in my field show a lot of movies. I don't, because of this. I hate to, move the slides and play them and so on. But this was one of our simulations. So you are seeing a 3D simulation of binary star in general relativity, and this is the mass density. But we actually, it's pretty obvious what is going on here. But what I wanted to point out is that this simulation actually span a large fraction of the entire space-time. So it's a simulation in time, in 3 dimensions. We cover area from the regions from the strong field region, where black hole is in this case, to the wave zone. So we are really computing numerically the space-time and the matter fields that are in this space-time, including now magnetic fields, neutrino fields, and so on and so forth. So these are rather complicated simulations. And this is the picture of our current understanding of the process. We could spend a lot of time in this slide, but I don't have it. But essentially, you have two neutron stars that are driven to coalescence by gravitational waves. Thank you. And so this is mostly gravitational interaction, but of course the neutron stars also are there. There is a pressure, and they are there mostly because of nuclear interaction and quantum mechanics. They are quantum mechanical objects. That's another beauty. Okay, no problem. It's small enough I can point to things. And then the moment that they fuse and flash and fuse together, you start to have things like shock waves, high temperatures, and so on. You produce neutrino. Some of this material gets unbound, and you have this. Some of this material gets also ejected from the system. And then what happened afterwards is mainly governed by, magnetodynamics, weak interaction, nuclear interactions, complicated microphysical model. This all goes into our simulations. And in particular, these matter ejection are what produce later the so-called kilonova. And even at a later time, for instance, if there's a black hole that is formed, not always a black hole forms, can form, depending on the masses and so, you may have an accretion disk with a black hole in the middle, and you have this development of jets. You have also interaction of this ejecta with the interstellar medium. So all this we are trying to describe as consistently as possible with our simulation. And you see it takes various spatial and temporal scales. That's the challenge. So I will flash a few results and then detail some of those later on in the talk. So what we have achieved in recent years is the very complete and precise model of the entire gravitational wave that is emitted by this process. This is an example of it. And you see it's a broadband spectrum from 2 Hertz to kilohertz and cover essentially this long, or the last part. So this is the band of the detectors, but it actually starts much earlier. It covers this very long spiral motion that is predicted by post-Newtonian theory. And then as you emit gravitational wave, this is a catastrophic process. As you emit gravitational wave, the orbit shrinks, you accelerate, and you emit even more gravitational wave. And you go towards merger, which you typically we simulate with full simulation. So the early part is really needs to be done with analytical methods in general relativity, and I will say something. And then as they, as they collide, if there is a remnant, you get these very high frequency waves which have not been detected yet, but they are also rich of information because they tell something about this very dynamical neutron star remnant. So in the first part of the talk, I will describe how we model this and what are the predictions, the interesting thing also for observations. One of them is the possibility of constraining what neutron stars are made of. So particularly the way that we do it, which I will describe in some detail, is through the detection via the gravitational wave of the tidal interaction of these two stars. And if you have a inference on or an estimate of particular parameters, you can actually map it back into the mass radius diagram and actually obtain constraining the mass radius diagram of neutron star, which in turn tells you, for instance, which models for the nuclear matter are excluded or compatible with observations. So this is a game that has been played with real data. So it was known before, but as soon as we had data, we play data. And today, several work have been done. And from this gravitational wave observation, the rule of thumb or the number that you have to remember is that we can constrain the radius of an equilibrium neutron star with 1.4 solar masses at around 12 kilometers plus minus 1 kilometer, which excludes a number of models for the spin density matter of the neutron star. This claim, so this is the same plot as before, but here we have folded in some other data, in particular the minimum maximum mass from pulsar observation and some nicer observation. So the take home of this plot is just that at the moment the pulsar data are actually much more constraining, and by that they also carrying their systematics. So these are identical analyses of multiple data. So nice gravitational wave. Also, the kilonova is folded inside here. But the two diagrams differ because there are two different analyses of nicer, which implies systematics. And you see that the green area changes quite a lot. So at the moment, the gravitational wave constraints are possible, but they are just compatible with pulsar data, which instead gives the main constraint to the mass diagram, and then give you a equation of state of high density matter. The other thing that I'm going to talk about are these mass ejecta that I mentioned before. So why they are important? They were proposed long ago, in particular from collision of neutron star and black holes, as a possible site for our process nucleosynthesis. So how to produce heavy elements. You need very neutron-rich matter, and actually, for many years it has been. You could read in textbook that very heavy elements, or our process elements, were produced by supernova explosion. But actually, this is not fully true. The most modern simulation of supernova show that at some point you don't produce all these three peaks of their processes, and instead this type of neutron stars are much more neutron rich. The dynamics is slightly different, and it's established now by many simulations, different methods, that you can easily and standard way produce all the elements up to the mass number 200, so third process peak. What happens is that you have this ejecta, neutron rich, you have rapid neutron capture happening, seed nuclei form, and then they decay by beta decay to the value of stability, and you get the elements produced in this ejecta. As a byproduct of this process, you have some thermalization process that actually in the fluid actually shines as a kilonova. Again, this was predicted long ago, but it was firstly observed in 2017, and since then many groups have started to work on it. So it's similar to a supernova for many aspects, but it's dimmer, so it's a bit more challenging to detect. And I will talk a bit about what's the dynamics that can produce kilonova signal. I want to flash a couple of other results that actually were obtained thanks to our simulations. So a few years ago, 3 years after the 2017 merger, a group, I think these are Chandra observations, detected some X-ray flux in excess for the source of 1920x1080 that are not compatible with the jet afterglow that has been studied in much detail. And so the question is, it's just a few photons, but the question is what it could be. And it turns out that a explanation is that this rays of the flux is actually consistent with something that can be called kilonova afterglow. So it's synchrotron radiation, similar in mechanism to a jet afterglow, but actually produced by the ejecta breaking into the interstellar medium, and it's produced by a very particular component of the ejecta that has high speed and that is ejected really during merger. So the very first component, the very first fast part of the ejecta that is launched away, and these lines come from our simulation. So this is a very robust prediction that has to be confirmed because there are no other observations. So maybe it was actually not true, but the prediction is there. So we do expect that years post-merger, we will see in X-ray and radio some signal due to this kilonova afterglow. And finally, I want to advertise not a super recent work, but a very nice one by Albino Perego in Italy, and many other people, which use this simulation and built from this first principle simulation an entire chain of other simulations. So they calculated the nucleosynthesis, they calculated the spectra, all theoretical, all first principle in some sense, and they managed to reproduce this the spectra here. And in particular, there's a feature that you see there, this little dip, which in a paper by Watson was identified as the feature of strontium from the kilonova 2017. So this is very nice because you actually reproduce it theoretically. And it's still debatable whether this is exactly due to that, but it was the first time that the entire chain, with some approximation on the way, of course, was done. Okay, so I will spend some time talking about gravitational waves. I spent some time in my life doing this, and this is the picture that we have in mind. So the main idea here is to solve the two-body problem in general relativity, which is very much more complicated than the two-body problem in Newtonian physics. But there are some elements in the way we approach it in modern times. There are some elements that actually go back to the Kepler problem. What we do, as an overview, what we do, we combine analytical methods in relativity with full-blown simulation, as those that I've explained. The scheme is typically this. This is the standard approach. So depending on the mass ratio of the binary and the separation, you can apply different, you can have different approaches to the problem. So when the separation is very large, and basically for any mass ratio, you are in a weak field regime, you can apply, of course, post-Newtonian theory. It means you are expanding on the Newtonian solution to find correction in V over C. So the velocity, the relative velocity of the binary over the speed of light. And this is also an expansion in the gravitational potential because of the virial theorem. But this approximation, of course, breaks when the motion gets somehow faster and faster and faster. The approximation gets worse and worse and worse, even if you add many post-Newtonian corrections. When the mass ratio is very large, so you have ideally, say, a curved black hole and a little object, then you can use another perturbation theory, which is valid for any velocity, and that's called the black hole perturbation theory. And here's the issue of self-force, which you have also in electromagnetic. So the little point doesn't follow, the little point mass doesn't really follow geodesics, but it has, you know, it also feels its own field in some sense. And that's something that has been also developed in recent years. But there's a region where, of course, you have high velocities and comparable mass ratio, where the only way is to use this simulation set to study two black holes merging or two neutron stars. Now, in 2000, Thibaut Damour proposed a way or a framework to have all these different methods together. And the basic idea is to develop, it's called effective one-body framework. And the basic idea is to have an Hamiltonian formalism, where you have an effective Hamiltonian for an effective particle that instead of moving, you know, in generic spacetime, it moves in an effective method, which is, say, Schwarzschild-Doppler-like. So it's a sort of, in principle, geodesics motion, but in an unphysical space. And this unphysical space is found by mapping the real problem into this effective problem of Kerr and the relative motion, effective problem of Kerr, particle into Kerr. And this is pretty much the idea of going, the Newtonian idea of going considering the relative motion and having a particle in an effective potential. So it's the general relativistic extension of that idea. You have an Hamiltonian, which you can map to the real Hamiltonian, and then you include a radiation reaction due to the fact that energy is moved away, is transported away. So this is the modern way of putting everything, of approaching the problem. And it is also interesting because you can use, within this framework, you can use perturbative result and numerical result in order to improve your Hamiltonian and radiation reaction and obtain a very faithful description for any binary in any regime of the motion. So that's what we use. And actually, this framework provides the first prediction for the entire waveform that has been detected in 2015 with the inspiral-merger ring down, the famous result of LIGO 2015. This was predicted 15 years before using these ideas, an early version of this formula. Okay. The other approach that we use is numerical relativity, and it's not just numerical relativity, it's based on 4 pillars. So if you want to solve general relativity on your computer, you have to think about different things. One thing is that you have to formulate Einstein equation as a Cauchy problem, so initial value problem. And this is, you know, more mathematical aspect of the field, but you really need to think about a well-posed initial boundary value problem for Einstein equation, which is tricky. Some results are there since more than a century, but it's a very active area of research by itself. Then you need to think about coordinate. You have to introduce some coordinate, and write this equation in form of partial differential equation. And here's where the art comes in, because you cannot just pick some coordinate. You have to pick good coordinate. For instance, coordinate that allows you to evolve black holes, to handle singularity, which the computer does not like, and handle the gravitational collapse, handle the movement of a black hole on a numerical grid, and so on and so forth. Einstein theory does not prescribe which coordinates are best to use. And this is the artistic part, in the sense that you have to think and provide extra equation for the evolution of the coordinate in such a way you can actually deal with black holes, for example. And then we have a part which is more numerical, where we need to develop numerical methods for this set of PDE, and also this involves also using adaptive grids covering different multiple scales. So we use AMR technique from relativistic astrophysics, but some of these methods have been developed dedicated to the problem, for instance, of binaries. So it's not that you just take a package that is there and you use it. Many of the groups that are doing this work, they have to develop their own complicated code. And finally, this code has to run on some of the largest supercomputers that exist, because it's a four-dimensional problem without symmetries. So you need a lot of computer power. And nowadays, all the computer power is moving towards, say, heterogeneous architectures. So we need to port our codes to this type of architectures, which is a sort of engineering part, but this is something that we have been doing. I'll say something on the very end about it. This is the result of a few years of work. Every point that you see in this plot is actually a three-dimensional simulation. And you see they cover different resolution, they cover different number of orbits, and different spin, mass ratio, masses, different model for the equation of state, including microphysical model. Now, this is part of a public catalog that we have put together. It took years to put it together, and now this is the largest catalog of binary neutron star waves that are available to the community. And we have, here there are only a few, but we actually have about 500 different binaries, simulated 500 different binaries with different level of physics and precision, of course. And are related to that. We also release ejecta data and so on. So if you want to have a look and actually do astrophysics with some of the data, these are all in this other Jena community. Okay, so back to the physics. I mentioned that in order to constrain the high density matter, we measure tidal interactions. So how do we measure tidal interaction in these things? Well, what we measure are log numbers, or relativistic log numbers. And what these things are, this is illustrated by this little equation. If you have a star in an external field, the external field can be decomposed in multiple. The first one will be the quadrupolar multiple, so we'll have two indexes. And this external gravitational field will induce a deformation in the star, say a quadruple. The proportional, so it's a linear response type of thing, and the linear response is precisely given by this log number, or related to that tidal polarizability coefficient. So they are called like this because it is exactly as in electromagnetism. You have some material, you have the electric field, the material polarizes, and star polarizes to an external gravitational field. There's an entire multipolar set of this, the quadruple, L equal 3, L equal 4, and so on. And these enter, as we shall see in the next slide, these enter the description of the dynamics and the wave. But before showing that, this is the mass reduced diagram for many equation of state, as you know it. But this you can translate it into this plot, which is a plot of the quadrupolar tidal polarizability parameter as a function of the gravitational mass. And this type of mapping is what you use to map an observation of a gravitational wave, in particular measurement of the tidal polarizability parameter and the mass, into the mass reduced diagram of the neutron star, so to obtain this constraint that I have shown before. So how do they, by the way, this is a very old story. the first description of this type of things comes always from people that more 1982. This is an amazing paper which everyone should read, but one in a couple of pages it just sketches all the theory, and it's all there that people have taken back in around 2000. The interesting thing is equation 12. To say, okay, I don't really want to calculate it. The tidal polarization is 1. Not true. That's the only mistake. That is because okay, and so then this I don't have a slide, but basically this tidal probability parameter are the coupling constant of tidal interaction. So they enter. There's a term in the Hamiltonian, already an Hamiltonian level, that is parameterized by this coefficient, and they enter also as a leading order in the gravitational waveform. So from direct measurement of the phase, this is what LIGO does and Virgo does, you can estimate that. The difficulty of doing this is in this plot. So this plot is the Fisher matrix plot, but it doesn't show the Fisher matrix, it shows the integrand of the Fisher matrix. So it tells, as a function of frequency, where the information is in a waveform, in which frequency range you get information of certain parameter. So for example, at relatively low frequency in LIGO Virgo band, you get information on the Chirp mass. Is this red course here? Huh? So you accumulate many cycles, and the Chirp mass is proportional to this many cycles. So that's where you get information. Then you get information from mass ratio at a little higher frequency, and SNR, and so on and so forth. Spin, which enter at higher post-Newtonian order, so you have higher frequency, gets information on spin and so on. But you see that tides are here. So the information accumulate at very high frequency. It means in the very last orbits of the binary. So it's clear why. These are short range interactions. So at the Newtonian level, they go R to the 6. So 1 over R to the 6. So it's a high frequency type of information. And they are also decoupled from all the other parameters, first approximation. But you really need to have a very precise waveform model in the very high velocity regime in order to extract information from this tidal polarizability parameter and then on the equation of state. So that's the difficulty. You really need to combine analytical method and a numerical method to have very precise waveform models, and then from these waveform models hope to resolve the waveform at the observation at very high frequency and extract this tidal parameter. So this waveform model exists. This is our latest effort. We work within this EOB framework. This is all public available, and this is basically the state of the art at the moment. So the version is called DALI, because we started with the version called Giotto that dealt only with circular orbits. But then we say, okay, there are not only circular orbits. So the DALI version actually deals with generic type of motion in general relativity. So this is a model or a framework that gives you a prediction of things like dynamical encounters, scattering, hyperbolic orbits in general relativity with radiation reaction, which is completely different from Newtonian physics. And it also can handle generic bias, so to neutron star, to black holes, or a neutron star at the black holes. The reason is that we model in detail spin interaction, spin orbit, high order spin terms, precession, tidal interaction that I talk about, and the model has a fold-in information from simulation, especially in the very high frequency regime, especially in the post-merger regime, where you have either ring down emission from the final black hole or the neutron star remnant emission at high frequency. And it deals also with, so we are also working on extreme mass ratio binaries, which are somehow a bit challenging at the moment, but we do have waveform for that. It's all public available. Okay, and this is an example of what one could do. So Einstein telescope might become a reality in 10 years or more, I don't know. And Einstein telescope has a potential of detecting this very high frequency part of the gravitational wave signal. In particular, it has the potential of detecting both this inspiral and merger thing and the emission from the remnant. So we call this the full spectrum analysis. And so we have shown, actually, student Matteo Breschi, student in Jena, that finished a few years ago, showed that first of all, this detection in ET are possible with events like the one that we observed. ET would detect the entire signal. And he also showed that the detection of the very late part or high frequency part of the signal would actually give you the possibility of really constraining the entire mass radius curve in the entire diagram. So these are mock inferences of just one part of the signal for the magenta and the entire signal for the blue. And you see that the magenta is particularly accurate up to 1.4 solar masses. This is the masses that are injected in this mock analysis. But it fails, for instance, to capture the maximum mass. Whereas if you add also the higher frequency part, you have a very high, where you can capture the maximum mass and the maximum density of equilibrium neutron star in this diagram up to 10-15%, just one event. And 10-15%, one event like the one that we detected already, but with Einstein telescope. And this 10-15% hits already the theoretical uncertainty that we currently have. With one event in ET, like the one that we observed, we could have a lot of information on the mass radius diagram, and will be hardly do better because of theory constraints. So we have to work much more if we want to do better. This shows the potential of ET. It's really an high precision. It's an astronomical instrument, an astronomical detector, but at the same time, it's something I like to think about it like really like a high precision particle type of detector, like LHC or so, because that's the kind of precision that it can bring. Yep. No, so the gray is are current constraints that you have, and the other line shows how you would improve over them. Then these are 90% confidence region. Yes and no, because for a single event you have fixed masses. So the information that you actually maximize are the information nearby the masses where you're actually detecting. So you see both curves actually get larger below, because here you don't really constrain much, because the neutron here was 1.4, 1.4, something like that. So the maximum is really there. And then the magenta curves open up. It means you are more uncertain there for the maximum mass. But because the remnant reaches very high densities, the blue curve constrain much better the higher part of the diagram. Also, it's important to remember that this is a diagram of equilibrium. So you map back through this tidal parameter, you map back into the equilibrium. So this is a TOV solutions in general relativity, but it's an equilibrium spherical solution. Okay, and then what else can do? Einstein telescope and kilohertz gravitational wave. So these are all experiments that we have done with numerics and so simulation, combining simulation and Bayesian analysis. What you could have, for instance, look at the very first plot at the top here. What you could have, you could have two binaries, for example, that for certain masses, they are actually identical. But at very high density, you have, so if you talk to nuclear physicists, you say, oh, but there must be hyper on there, right? The neutron star matter must have hyper on its side. And so there are microphysical model of equation of state that are identical up to a certain density, But then depart from, say, the model with hadronic matter because you have hyperons. And typically the hyperons give the softening, so lower mass or lower pressure for the same density. Nuclear physics tells you you must have these hyperons. If you would have these hyperons and you would compare the signal, for example, to just to a model that does not have this hyperon, then you would see that, for instance, for the inspiral, you could have an identical signal. Here, these are for different masses. But if the masses are somehow fine-tuned but not much actually, the model with hyperon would collapse to black hole, for example, whereas the model without hyperon would not collapse because it has more pressure. And so the high-frequency gravitational wave could give you a hint whether you have hyperons in this remnant. And you can formalize this. You can do this exercise and make an inference and show that actually it's true. So you could, in principle, measure with Einstein telescope such the effect of hyperonic degrees of freedom in the remnant by using kilohertz gravitational wave, which is quite amazing. And similarly, you can do it. This is a similar experiment in which the microphysical model for the matter has been chosen among 3 with different nuclear mass, which means you have different thermal effects. And we show that you can actually, in principle, AT has the sensitivity to discriminate between different model with different thermal effect or nuclear masses, which is also quite impressive. I didn't believe this result when they showed, but it's correct in the end. And you can do these things with Bayesian analysis. But the big open question is that all this here, of course, in a mock experiment, you have control of everything. So you compare A with B. But in an observation, you don't. You have just a signal. And so the question is, okay, how can we have an ambiguous procedure at the data analysis level that actually allows us to claim from an observation that there was hyperons in the remnant? This is an open question. We don't know how to do it, simply because we don't have a reference model in nature. So we don't know what's the equation state of this things at high density. But in principle, ET has this sensitivity. Many of these effects are also degenerate, so it will be hard to pinpoint them, but there's work ongoing in developing strategy to do that. Okay, how am I with time? Usually I'm better, but I have 10 minutes. Okay, so in the last minutes, so 10 minutes, I want to talk about how we connect with simulation these remnants, actually the dynamics to the actual kilonova observation. And so this is the picture that I've explained before. And so the first thing that people figure out in my field is that it's not that this thing collide, there's a mass ejection, and then there's a kilonova. It's much more complicated. So you have different, depending on the stage of the evolution of this remnant, you have different type of ejection mechanism. So the very first is this thing called dynamical ejecta, because it's emitted on dynamical timescale in a phase of the dynamics in which the dynamics is mainly driven by gravitational wave emission. So it's a very early stage after merger. And this type of ejecta can come from just the collision of the two cores or from centrifugal effect. This depends a bit on the mass and mass ratio. But if it comes from the shock of the two cores, actually there's a sort of bounce between the two cores. The second, typically the first bounce is the one that determines this dynamical ejecta. And this is the one that has also this very high tails that do the synchrotron emissions of kilonova afterglow. And this has been characterized. We have characterized it with many different type of simulations and classified in some sense which binary give you dynamical ejecta which is more shocked, and which binary give you dynamical ejecta which is more from the centrifugal effect. This is important because the tidal one is typically colder and neutron rich, whereas the shocked one has been reprocessed typically by neutrino, so it's and comes from a shock, so it's warmer, a higher temperature, and it's more proton rich. So this determines the color, for instance, of the kilonova. And something that was very important that we figure out around 2014-17 is that neutrino, including weak interaction and neutrino interaction, is very important already at this stage. So as soon as the star crashes, the temperature goes high, and you have a lot of neutrino production, and this neutrino propagates in very dense matter of the remnant, and they are reabsorbed. They don't just fly away. And so this is an example of the same simulation, which has two different ways of treating neutrino. Here we just cool them out, so we leak them out. And here we cool them, but we also reabsorb according to a certain scheme. And you see that the electron fraction, so the composition of this dynamical ejecta as a function of the polar angle is different. You have more proton-rich type of ejecta, and you have also different distribution. So both composition, thermodynamical, and kinematical properties of the ejecta heavily depends on neutrino interaction, which means that also the kilonova will shine differently depending on, say, your numerical scheme for the transport and what you put inside. This was very important to realize, and now people have developed very sophisticated neutrino transport scheme, almost at the level of supernova explosion, where it's critical to have proper neutrino simulated. Then, after this first phase, you typically end up in this situation. You have a big material, a big disk, massive disk around the neutron stars or a black hole, depending again on the binary. And you see this is again, the composition is very different. The compactness of the disk is different. The amount of proton or neutrons is very different depending on how this disk was formed. And an interesting observation that we had in this paper is here. If we calculated the mass of the disk for several models, and we have plotted against, this is one of these tidal polarizability parameters, that is the dominant effect entering the Hamiltonian and the waveforms, and you see that there's a strong correlation. So this is somehow unexpected, but this is because this is also a measure of the compactness of the binary, of the previous binary, and reflects or correlates with property of the remnant. This is very important because this opens the way to, for instance, doing multi-messenger analysis, joint analysis. So if the gravitational wave gives a constraint on lambda, through this numerical relativity data, you have automatically a sort of constraint in the disk or a prediction of the disk that the remnant can produce. And so this type of information is now, by some group, folded into their multi-messenger joint analysis of kilonovae and gravitational waves. And at this point, there is a point in which is after 10 or 20 milliseconds after merger, where basically all the gravitational wave become inefficient. So the energy is all washed out by gravitational wave, and the object is sufficiently spherical, if you want, or sufficient stationary, such that the gravitational wave are not more efficient. So we say that this is the gravitational wave dominated phase is finished. And then the dynamics there becomes governed by other processes, which typically are neutrino cooling and gravity, which tends to, of course, bring the system to collapse, but opposed to viscous processes. So neutrino heating, magnetic turbulence stresses that instead tend to, expand in some sense the remnant. So the fate of this disk and how much mass of this disk is actually ejected depends on this very detailed balance of this multiphysics type of problem. And the bottom line is that if the disk expands enough, then it cools down, and then a nuclear recombination starts this massive winds from the disk. This is the largest type of ejecta mechanism. Before that, this is calculated from a simulation are the time scales for the gravitational wave emission and the neutrino emission in this case. And you see that after about 10 milliseconds, other processes than gravitational wave take over and dominate the dynamics. And in the first phase, if you have a remnant, you have typically this, this is, I think you know better than me, you have the spiral type of density waves, which are in many astrophysical problems like galaxies, for example, that in this case, from the remnant, transport angular momentum outside. So they transport angular momentum from the remnant to the disk, then the disk expands and release more and more matter, depending how strong the spiral waves are. And you produce a wind in this way. So here you get a second ejection type of mechanism called spiral wave wind, which contributes also to the kilonova. And finally, this also, because the angular momentum is never enough, this also finishes, and then you remain with the disk that continue to emit for other processes. And so the message was that you have different type of ejection mechanism, and each of that contribute to the final kilonova, for example. So these plots show in points the different contribution of this ejecta mechanism. So of course, this wind is not upper limit because we don't have so long simulation. This would happen in timescale of seconds, which have been reached in one simulation by some Japanese group, but they're still quite challenging to reach. For basically all the data that we could collect compatible to the event of 2017. And the boxes, the blue and the red boxes, are instead what has been inferred from the kilonova analysis using simplified models. So typically simplified model means spherical models, basic physics of the kilonova, very, very simplified, and at least two components. You need the high opacity and low opacity type of component to feed the data. And then you can infer the mass of the ejecta, you can infer the velocity of the ejecta, and the average composition. But you see that none of the simulation actually fits the boxes. So this tells that, okay, the fit is good, but the model is not great, right? And so it means that the actual mechanism of ejection and kilonova emission is much more complicated than the simple two components spherical model that have been employed so far. And of course, doing much better than that is a challenge. So we are working on it, but we need combination again of numerical data and more sophisticated analytical methods and approaches. And nowadays also people are starting to do full 3D radiation transport simulation of the ejecta itself. And this is the little application. So you remember this plot. So I said before that the disk correlates with the standard tidal parameter. And it turns out that to explain this data, actually you need the disk. There is no, you need some wind from the disk. There's not enough. It's so bright and also blue, and such that only the dynamical ejecta, for example, cannot explain this light course. So you do need disk. But if you do need disk, let's say you need a minimum disk mass, that it means that you need a minimum, well, you put a lower limit to this tidal parameter. And we have played this game. So because of the kilonova observation and because of this information, we can put a lower limit to this tidal parameter. Here is a function of mass ratio, it doesn't matter. You can put a lower limit to this tidal parameter with the kilonova data. But of course, in this particular, this is the early analysis, the early gravitational wave analysis was actually giving an upper limit on lambda. And so combining the two things, we actually can reasonable measurement of something that if you use only one messenger would be just a lower or upper limit. So this is kind of the power that is in this multi-channel or multi-messenger type of science. And the key thing are these arrows. So these arrows, so the key ingredients are these arrows, and the arrows is a very precise waveform model, which can go and is very faithful up to very high frequencies. and also very precise and targeted simulation in this case that allow to establish this sort of quantitative relation. So this was the idea that we put forward in 2017, but we have actually realized it later in a paper by, again, Matteo Breschi, in a full Bayesian analysis. So we have made it formal. We did obtain the equivalent of this sketch results in a full Bayesian setup. This is a bit more recent work. So another student, there are many Italian students, my God, they are very good. Another student recently actually performed the first simulation of the ejecta evolution with radiation hydrodynamics with an online nuclear network. So what this means is that you evolve radiation hydrodynamics and you have an heating term in the equation that comes from the fact that at every time step of this radiation hydrodynamics, we are actually solving the full nuclear network. You calculate how many isotopes are produced at every time step. Usually these things are done in post-processing, but if you do it in post-processing, you lose the feedback of the nuclear heating rate on the ejecta itself. So you have to assume some symmetries, and you have to reduce a bit. This is very expensive. It cannot be done in this way in 3D. This is 9,000 isotopes and reactions, so it's very complicated. But within some symmetry, it's possible to do it, and we can calculate in a reasonably consistent way the entire evolution of the different elements. So the blue line, for instance, are neutrons, and so on and so forth. I don't want to discuss this in much detail, but essentially nucleosynthesis happens in the first second of evolution of this ejecta. And a byproduct of that came out this week is that for the first time in these runs, in this simulation, we actually okay, this is the nucleosynthesis, so you have the three peak of our processes. But here, we identified in this simulation nickel 56, which is very well known to people doing supernovae and was not identified before. So we've proven through simulation that part of the ejecta is sufficiently proton rich such that down to nickel 56 and the entire chain with ions and so on can be actually produced. And we are looking into possible signature because we know that in the supernova observation, this gives very precise and very well-studied signatures in the light covering the spectra. So we are now looking here. We have proven that we can produce it with this type of mergers, but we have to look at what could be the potential observation impact of this. And the key thing why people didn't do before, the key thing is again neutrino. So this latest simulation that we used employs a more sophisticated neutrino scheme, which we don't know if it is correct, but it's more sophisticated than what we had before. Of course, we could go even further, and that's what we are going to do. But essentially, there's a strong dependence on the element formation, also in nucleosynthesis, depending on how the neutron and proton rich are these ejecta, and this directly impacts the nucleosynthesis. Here is an example with some older scheme, for instance, and you see that if you just leak out this orange thing, if you just leak out neutrino without reabsorbing them, for instance, you underproduce this nuclei with respect to streams that instead include the absorption of neutrino. And this is something that we have to look much in detail because the detail of these things make it then a big difference at the moment of looking at observation. And yeah, so I don't want to describe this in much detail, but basically you see these are pictures of the ejecta in some, so the orbital plane is here, this is a section, and you see this is the composition of the ejecta for two different schemes. So you already see that there's much more neutrons in one and not in the other. The distribution itself of the composition is very different and so on. And this is an histogram on how this is electron fraction, so how protons reach out this ejecta. You see that some scheme can push this proton rich ejecta to very high values. This is limit equilibrium, and this is what produces this nickel feature. Okay, this is actually my second last slide. So I mentioned at the beginning that nowadays they are changing all our computers, and computer power is increasing, but you need to use GPU. So what we did a few years ago was to start working on a new generation of numerical relativity code. This is the result, and it's there. It will be public soon. You see, there are many things here, but essentially what this code does is to scale up to the 5 cores. And that's the only way that we can take it. We can include more and more physics and take advantage of new architectures. So this is based on Athena++, which is a public available relativistic hydrodynamic code developed by the Princeton group, used by many people, probably also around here. But we developed the full generativistic version on dynamical space-time, adding all our methods and so on. We can produce nice waveforms and so on. And also a couple of weeks ago, there's already the next version of this that actually works both on CPU and GPU. It's called Athena K. And with that, if you look at the paper, we have benchmarked on the largest supercomputer in the US, which is an exascale computer, and works like a charm. So we hope to tackle bigger problems and all these physics details with these new tools now. Okay, here are my conclusions, which I'm going to read. So this binary to start an extreme astrophysical laboratory, as you guys know better than me, and these are very rich sources of different multi-messenger emissions. The theoretical modeling of this is absolutely essential for the interpretation of these signals. But I like to see the thing, or at least my motivation is to see the thing the way around. For me, this is the perfect playground for a theorist, because I can play with all the interactions that are at play there, and actually do something useful, like predict waveforms or kilonova light pulse. So for what concerns the gravitational wave models, these are also necessary. I didn't talk about this, but LIGO, Virgo, and Future ET, they work with match filtering, which means that you look for gravitational wave signal that you already know, which means you need to know a very precise model of what you are looking for in order to find it. And what you can do with this gravitational wave, so you need the waveform just for the experiment to work. But then you can also do physics and from a detection, and for instance, you can use it to constrain neutron star matter through this tidal polarizability parameter and put constraint on the mass reduced diagram. So rather accurate models are in place. For what concerns, say, ET accuracy, the systematics are not yet under control. ET can provide very precision measurement, but again, you need high precision waveform to do this high precision measurement. And these are not yet fully under control. So if you have a signal like the one that we detected in ET, nowadays will be fully dominated by systematic. You will not be able to make the physics at the precision that you could in principle. And also this new next generation detector will be sensitive to kilohertz gravitational wave. You could probe even more effect of extreme matter, high temperature, even higher densities, although some unambiguous procedure for the detection are not yet available. For what concerns the kilonova in this case, so again, this 3D multi-physics simulation are crucial to interpret this electromagnetic counterpart. So remember this plot where the box didn't match the points. And nowadays, this simulation incorporates general relativity, magnetic hydrodynamics, these microphysical models for the neutron stars, neutrino transport, and they resolve, as I mentioned at the beginning, an entire part of the space-time. And what we find from this is that kilonova actually shine from this multi-component and an anisotropic mass ejecta, and some of these properties importantly correlate with the binary parameters, so the disk mass and the lambda temperature. However, So there is no simulation nowadays that can quantitatively fit what has been observed in 2017. Although the main features or the qualitative features are all explained, but there's always this factor 2, 5 to 10 that is missing here and there. But my prediction here is that if we continue like that, in a few years, the nuclear and atomic uncertainty that goes into this problem will be actually dominating the error in our predictions. So I think we are doing very good, very rapidly. But of course, we need input from nuclear physics and atomic physics, and these are very, very uncertain. So our goal at the moment is just to, be at a stage where they are the problem, and not us. Okay, thank you for listening. This one?
So if I make the M1 model,
yes.
The one that's now tested.
Yes.
But around the mass number of 150, all the two models are completely against the
yes.
solar.
Yeah.
The solar environment.
Yeah, so there are different things here. On one hand, we don't need necessarily to reproduce the solar abundances because we don't know, right? This is just to guide our eyes. And the other thing is that, of course, to run this simulation, we use data. We use some, nuclear data and so on and so forth, which are, as I said, the very last thing, they are not perfect. And so it's also possible that at this point we are already starting to see uncertainty on the nuclear physics side. And the data that we use is not, of course, the latest possible and so on, because we try to talk to nuclear astrophysicists, but it's not always possible to have their latest thing or understand what's the best thing at the moment, or so on and so forth. So we are not too worried about those, in the sense, not yet. Yeah. So this number is in literature. I don't have it on top of my head, but just to give you a comparison, this 40 megaparsec event that we had. So it had, I think it had SNR around 40 in LIGO and Virgo. With ET will be on hundreds. So it's a big jump. It's a big jump. The sensitivity curve goes a factor 10 below, so you have a factor 10 cube. So what we typically try to do, so first of all, there's a difference between doing also some binary black hole simulation. And the binary black hole are this type of, I don't know, this is a perfect macroscopic object, particles, right? But macroscopic particles. So there you have mass and spin, and that's it. So for binary black hole, talking about parameter space is fine, and people do it. And you have the two spin times 3 components and the masses. This is for binary black hole. For binary transistor, you start from there, but it's way more complicated because you have physics assumptions. So you have to start to say, okay, which which nuclear physics model I want to assume in order to describe the matter. And then you have, and then you start to have, you look at the market and you say, well, every nuclear physics group tells me that they are the best models. So I have to try as many as possible nuclear equation of state in my simulation that I can, as different as possible. And so this is the colored on top there. So we are now available a certain number, and we try different of them for the given masses and spin and so on. But then there's more. When you talk about spin, well, this is not really a sort of point particle thing, right? This is really an extent. So you have to explain, you have to make a choice how, for instance, the initial data of this, what's the velocity field in the star in the initial data of your simulation. So then you can make different hypotheses there, and they give different spins, for example. So what we do at the moment, most of these simulation are calculated either assuming rotational flow or assuming a variation of it that in a paper we call constant rotational velocity, but it doesn't matter. The key thing is that this choice is entirely based on the fact that to start the simulation, we need to solve the elliptic sector of Einstein equation. So we need to solve the constraints. And when you make a choice on your velocity field, well, then you may have more or less complication in solving the initial data constraints. And these are the only two choices that we know that we can assume in order to solve the constraints. So we have formalism, and so on and so forth. So then when we simulate, we say, okay, we want a neutrino, but where do we take the reactions, or which reaction we put it? So in this case, I would say that talking about a parameter space is more complicated, and it's not something that is very well mathematically defined. And we really go and assume certain models, which we think they are reasonably correct. But then we need to explore with variation of physics. That's also another game that is played here. You try to vary just a component of the physics and see if you have something, for instance, can be detectable or can be observable, or if you have a so it's very large in this case, where it's actually infinite, right? It depends on your choices. Yeah. Okay. Thank you.
Because the predictions for nucleosynthesis, everything here. Put the keys downstairs.